ठीक है Just a second. Oh, back to the channel. Okay. So I will kind of start from the same point we left yesterday, but today I will have to cover a lot more things, so I might be going a bit faster. But this PDF, the whole thing is a single PDF. I will be sharing.
Recording in progress.
With the coordinator, you can request him to send a copy rather than me sending to everybody. Okay, we'll talk a little bit about the detectors. And CCD, like all of you know, is the most modern detector now. I will not diverge into CMOS detector, although nowadays the most modern cameras, including Sony, etc., they are not even using CCDs. They are using what we call CMOS detector. But CCD is a pretty simple device. It's kind of an array of so it's an array of pixels. So this is a typical CCD, and usually this is the largest now available is, and there are not, of course, drawing to the scale, and each of these is called pixel. This is actually a silicon chip, raw silicon chip, on which you make these as pixels which are sensing the light. So essentially, the book which I referred the last slide today is a nice book which explains this phenomena very well. So you should read it. So essentially, what happens? Just like a camera, here also it's a camera. When you give an exposure, suppose there is a galaxy here. This is a galaxy, and the rest of it is dark. So what will happen? These areas, these pixels will pick up the photons. The other part will be sky. So usually the photons will be more where the galaxy image is there. So you take an exposure, 1 second, 10 seconds, depends, which I discussed yesterday. Then the picture is here. So now CCD acts like the best example is like they are all, let's say, buckets. And this galaxy is like a rain, which is coming from a cloud of that. So only these buckets will be filled, these will be empty. But now the thing is, after the exposure is done, of course, in case of bucket, the rain is continuously falling. But let's say rain falls for 10 seconds and stop. Okay. So 10 seconds, some of these buckets have filled, some have not. But now that information has to go on the computer. So how do you do it? They essentially generate clock pulses like this, square pulses. And these pulses are moved in such a way that you read wherever the layers are filled or not filled, that information is slowly carried like this first and then like this. And here on the chip there is an amplifier because these are charges actually. Like buckets, actually these are the charges which are filled in the wells. And these charges ultimately form a current because you will let the charges pass through a resistor and then amplify because there is a very small charge that gets amplified. Becomes a so Once that happens, you have collected the information. Now you have to, can you mute everybody there? Doesn't matter, you do it. No, do it because just mute everybody. Yeah. So then that information has to be transferred ultimately as an image, right? Which is what you want to do. So what will happen when you do all that? You process this, and it takes bigger the CCD. It will take more time because there is a process, and there are some losses. The charges are lost, so there are some efficiency issues. But eventually, it's a very fast way to make an image. And now remember, this is a digital image. On the computer, you can play around with it, process it. Like yesterday, I was mentioning, you take several images, you can stack them to improve the signal to noise by the square root of time advantage. So this is how the CCD works, and the CMOS is slightly different. The process up to the transfer of charges is same. Each of these pixels, they put the amplifier there, so it's much faster. But then it has some limitation. The sensitivity of CCD is much better than CMOS. But CMOS are mostly used in, so in astronomy, also CMOS has come, but usually people prefer CCDs because they can go very deep into the faint light sources. So this is actually a first image once it was taken. This is with a, not first image, this is with a film. Okay, so obviously films used to have very small. So these pixels, the sizes, even today the smallest size is about 9 by 9 micron, but films can have very small pixels. So that's a challenge, and slowly things are improving. And not only films, they're a big format. The astronomical films were almost the size of this 1 by 1 fit. But now what is happening? They are making mosaic. So this is probably the largest CCD, and then put several of them in a mosaic. And then obviously the time or the exposure, everything increases. So the precision has to be done. But you can do a very smart job of competing with the photographic film. So the good thing about digital is that the information is not lost, it is on your computer. And you can process it digitally. Like you can move the pixel, move the cursor, go exactly to that pixel, analyzing, and so on. I'll skip some of this a little bit. In contrast, the photometer is a 1D. So this is actually a 2D detector, right? Because these are 2 dimensions, so this is 2D. Whereas the photodetector is just a small silicon chip which will sense the light. So it's a 1D detector. But the advantage I told yesterday that photometry means you are collecting all the light, focusing on that chip. So this is where the photometer is shown, and you will notice that the light comes here. There is a flip mirror which allows you to see and focus the star. And then you make this flip the other side, the light goes further. This is a small aperture in which you make sure that the star is within this. Otherwise, you will have the skylight also come. This one we will not discuss right now, but this one, the Fabry lens advantage is it averages out the fluctuations. And then there is a filter. Today we'll talk about the B and B filters we mentioned yesterday. And this is here is written photomultiplier tube, but nowadays a photodiode is used, they are much faster. So this is actually a picture of the filter which we have, and the students here doing the MSc last 20, 30 years use this. The starlight comes from the telescope here. This is mounted here at the telescope, and these are the B and B filters. And this is the eyepiece through which you see. There is a red circle in which the star is centered. You focus it with the telescope, and then this is the flip. You flip it, and then the light goes further, and the display of the counts here. So you take an observation in B and V, and can move the telescope slightly so that you go off the star and you observe the sky. And then, of course, you can subtract the sky. Now, this is one of the early plots where all these exoplanet things started. Of course, today it's anything. It's almost more than 20 years back. You see, this is a standard star, which doesn't vary. Of course, there is fluctuation. But this is where we discussed yesterday that means there is an occultation taking place. There is a star and there's a big planet like Jupiter. It will decrease the light of the star and again come out. So these slopes are very critical because these slopes, if you analyze carefully, you can even tell the size of that planet and so on. So this is one of the early methods, but even today these methods are used. Except I mentioned yesterday, these dips, etc., have to be done in milliseconds so that you can do a very fast job to improve the accuracy. So usually transit is the phenomena used. In this case, this particular star, where probably there is an object outside in front of it, which is occulting. Again, there are issues here. The occultation can be along the diameter, can be at the edge, or may not be at all. Then you won't see it. So if it is edge, then of course you are not seeing the full dip. Okay, so most of the times that can happen, but also the face on. The star is here and the object passes along its equator. That is the ideal situation. Let me skip these things. Yeah, let's come to now the filters. Now, yesterday we talked about the spectrum of a star. Here, for example, you will see this white line here is a B-type star. Okay, and this, of course, in Sierra Dogs, you have seen a lot of spectra. Essentially, this curve, as my cursor goes, is a black body with a peak at about 4,000 angstroms blue. So it's a hot star, it's a B-type star. Now I have to, and that's why the colors are seen here. This side is blue. What are these? These are actually filters. Okay, so they are approximately 1,000 angstrom wide. And when I say 1,000 angstrom, it's actually a line across this. And it is, of course, a kind of a function. It's not a rectangle. Ideally, it should be a rectangle, but it's not possible to make a rectangle filter. So you assume this as a rectangle, which means this is a square filter here, square filter here. So the B is at 4,500 blue. The visible filter is 5,500, and at 6,500 is the R. There are other bands we will see, but mostly these B, and R. And as I discussed yesterday, at least two wavelengths you can use B and R, you can use B and R. And if you have more, then all you know, there are errors coming in. So what are the two errors? One is, of course, this is 1,000 angstroms, okay, each of them. So this 1,000 angstrom I am averaging out at the peak of this filter, which means I am not seeing the counts at each of these points. Rather, I am averaging this 1,000 angstroms into a single number at 55. So on x-axis there is an error bar. Similarly, this I will show you these error bars. On y-axis there is another error bar. Now you would have heard or even hearing some other lectures, there is something called Poisson statistics. So a quick way to explain that is, we did this experiment during 80 days. So you make a tube, black tube. Inside one side you have a detector, which can be CCD. Those days there were no CCD, a simple photo detector. And you have a light. LEDs were there even those days. So you make a simple circuit, or even a bulb. So essentially, this is your and you can have a switch here, switch, and this is your bulb or LED, it doesn't matter. And there is a potential. In this circuit, when I switch it on, I can vary the intensity. So what I will do is now, I will reduce the light inside that closed tube, and of course you are sitting in a dark room, so that just start sensing the light above the noise. So there is always a dark temperature of that tube. Some dark photons are continuously there. So suppose there is a count level of 10, 11, 10, 11, 12, continuously going every second. As soon as I make it minimum, now I call it as a just sensing. That's why signal to noise discussion was there. So let's say 10 is my average. And usually, because of Poisson statistics, the way photons come, it is 10 plus minus root of 10. Which means 10 plus minus square root of 10. So plus minus 3 fluctuation will be. If it is 100 counts, then 100 plus minus 10 will be continuously there. Now I switch on and make my sensitivity such that now my mean count increases with that LED light to say 120. So 20 is now my signal. 20 also will have fluctuation. Now what you do, you make an histogram. Now you're all physics and science students. Histogram is used in biology everywhere. Always the x-axis of histogram is the bits, right? And y-axis is the number of occurrence. So suppose I draw a histogram, and as I said, so I will drop out these things. We are concentrating only on this. So I said that there is a count of 10, which is my now, and plus minus root of 10. This is continuously happening. So because this light is inside the tube and I have a detector outside, which is sensing and giving me counts like that for the meters. And when I switch on, this becomes, let's say, it becomes 20. The signal is now 10 plus minus root of 20. Now this is continuously happening. So suppose I take this data onto your computer and wait for about an hour, then what will happen? I can draw a histogram. This is the mean count, which is 20. These are, say, 18. This side is 22, and so on. And this is number of times that is happening. So in 1 hour, you will actually make an histogram something like this. So all it means is that there are very small chances, very less number of occurrences when you have larger deviations. Most of them will be at. This gives an excellent test on how the photon statistics come. So this is called Poisson statistics, and the photons are continuously coming with that. That's why on the y-axis here, you will have an error from the start. Due to all reasons combined together. It's not just the atmospheric fluctuation. Even if atmosphere is not there, you are sitting on moon or on a space telescope, fluctuations will still be there because the photons are coming in a Poisson manner. And the fluctuations are root of the original count. So, so there are two errors now, one error on this side. So let's see, I have that plot here somewhere. This one. Now you see, this is the same plot which we showed yesterday also. Now I have sketched it with hand. This is B, V, and R. Okay, and the same temperature, different temperatures. These are the B, V, and R bands, 1000 angstroms, and these are the peaks. And now you can see that I have shown this x-axis error bar because we are averaging over 1000 angstroms. And y-axis, I just explained this intensity is because of the Poisson. So there are double error bars here. Now, the only way to improve the x-axis, and of course the y-axis will slightly improve, is to make more observations, not just being there. And then you move to what is called a spectroscopy. So this is photometry. When you go to spectroscopy, you are essentially sampling the same black-body curve in so you are improving the estimation of this curve. That is the basic concept of spectroscopy. So we will go to that. Before that, let's see some spectra. So this is a continuous spectra. Now, a good example in the library, you can see some basic good old optics books, where you will see that Newton is sitting with a prism in a hall like this, and a streak of sunlight is coming, and it is projecting a spectrum like this. This is very normal. This is called continuous. And why continuous? Because there are no breaks here. The color changes continuously from the blue side to the red side. And this happens if it's a tungsten bulb. So nowadays, of course, in your automobiles earlier, the bulb was filled with other gases, but nowadays you have much brighter bulbs called halogen lamps. So what is halogen? It only improves the temperature of the bulb higher and makes it more brighter. So usually halogens like fluorine is not used, but they may be using xenon or something. Sometimes the night you will see this fancy cars, they put these xenon bulbs, which are bluish. They hurt you, and they are very bright. But most of the things are now halogen. In fact, now the next level have come, which is LED. So it's even better because halogen lamp will also have a life because it has a filament and halogen is filled. But LEDs are much longer. And LEDs, again, white LEDs are there, but they are spread over somewhere. It's not as a laser. And LEDs Single one is not enough. So you would see them as a train of LEDs in the headlight. So slowly that's happening in all the automobiles now, including the new electric bikes, etc. They all have LEDs because their consumption is less and they are kind of bright, but they're still not as bright as a halogen light is. But they are very soon the technology is improving to make it as bright as that. So that is different from an LED. LED is a solid state device, so it has a transition between two levels, and that light is what you are seeing. And that light cannot be very white. It can be white, but it is distributed over some wavelengths. Whereas here it's a constant bulb, and it's like a black body. So if the constant bulb is at 2500 Kelvin, then it will be corresponding black body. But this is what you will see. But now suppose I take this example. This is a tube light, this is not a LED. In between, you see this line. This is a mercury tube light. So this is the mercury 5461 green line. There are some lines here, and here it's not clear here. Mercury, like sodium, has two lights, D1, D2, all of you have done experiments. You should know that mercury also has two doublets here. They are 5770 and 5790, 20 angstroms apart. In case of sodium, D line is 6 angstroms, 5890, 5896. Here it is 5770 and 5790. So these lines are sitting on a dark line. But actually it is not dark. I will tell you what it is. The problem is, in case of mercury, it has a lot of continuum. So mercury light, if this is my wavelength and this is intensity, there is a continuum white background on which you have this line. So this is 5461, this is 770, 5790, and these are the blue side lines. But this is what kills. Because in astronomy, you want the sky to be dark. So all the city light scatters up there, and if there is a dust, the sky looks bright and you can't see the faint stars. And that too, if the city lights are mercury, it is this is killing it. Whereas in case of sodium, in the same plot I can show, if this is mercury and this is sodium, then all you have sodium, just two lines here. 5890, 5896. Just D1, D2 lines. And rest, this is not there. So unless the astronomer is interested exactly on these lines, sky scattering is minimum because these things are not scattering. That's why, and more advantage is it consumes much less electricity. So most of the last street lights are going into sodium. But the new thing again is back to LED. Now they are introducing, even if you walk in the Ariba campus in the night, you will see these lights which are multiple LEDs. They are white LEDs and they are very bright. So that's really killing it again. Okay, so, but again, LEDs are even more cheaper to run than sodium. So essentially here what is happening, there is, the gas itself is emitting these lines like a star, which has an emission. But usually the star is like this. Why? Because star is a source like the halogen bulb. So in case of star, what happens? This is your star, which is like a black body. A star is like a black body at T is equal to whatever, 5000 degree Kelvin. But star also has color chalks. Okay, there are some color chalks. So star will have some atmosphere. We saw in yesterday talk. So this is the continuum part, and there are atmosphere around the star. So the light it has to pass through this, and this atmosphere will provide these absorption features, depending on which type of atmosphere is there. So in hot stars it is hydrogen and helium, so you will see only hydrogen and helium lines. And in cooler stars, more and more denser lines will come. And also, of course, the black body will shift towards the right because it's a cooler star. So this is the situation for a absorption spectra. These are laboratory, but this is actually what is happening in the star. So again, this is a popular way of showing. This is the, here is a bulb, or in this case, it's a star, and you have continuous spectra if there is no gas around it. But if there is a gas cloud, then you will see the absorption. And if the gas, some stars have excited gases which are also doing emission. So both present, but usually this is the situation, absorption spectra most of the time. Now, slowly we are going into the situation how to measure this spectrum with the instrument. So, this is my telescope. I just represent it as a bead, can be a lens or a mirror, doesn't matter. And the light from infinity, the star or galaxy, comes through a slit. I need a slit because I don't want the other light to come through, only the light from the star, a little bit of the sky. Then, usually, I will make a parallel section. That's why it's called collimation. Collimation is always to make a diverging beam parallel. So this collimator's job is to make a parallel section. And this is called a camera lens because older time this was a film. And this was like a camera, and you could, this lens purpose is to now refocus the thing on the film. Here we are talking about a CCD detector. So this inside, this parallel section is where, in case of neutron, it was not so important since just we saw the spectrum. So ideally, the prism should sit in the parallel section to see the spectrum. But you can put a grating or even other resolution instruments. We will go into that soon. So this is a basic spectrometer design. And here I have put it in color. This side you have blue, this side you have red. So spectrum will appear. This is just similar thing, but now remember I mentioned the star is continuously dancing in the night. It's not a single spot infinity, no. The star is continuously dancing because of the atmosphere. The starlight comes and gets twisted because of the turbulence in the atmosphere. And because of twisting, just refraction is taking place. So it is continuously, each ray, when it comes, at that instant, in 10 milliseconds, it is spotting here, here, here. So this is the actual thing that is happening. And of course, the concentration is at the center, but fainter dots are here. Because it's rarely that it is that far away, but mostly it is this. And this edge to edge, in a very good site, will be 1 arc second or even smaller. So most of the things like a city light, and here if you do this kind of measurements, there are ways to measure this. Seeing, I will define these things. Then it's usually 2 arc second or even less. Because the star is continuously dancing. One common question which usually can be asked in the vivas and we do it. Everybody's seen a planet, right? You have seen Mars, you have seen Jupiter with naked eye or with a binocular. And a star. Now the common question people ask is, you see this scintillation of this continuous twinkling in case of stars, but not planets. Anybody who wants to answer this, why you don't see the twinkling in planets but not stars? Any reason you can think of? Love stars? You were saying something, stars.
Stars are far away, they appear as point sources of light. Planets are
Second part of your answer is correct. Stars are far, planets are also far. That is not the question.
planets appear at extended ranges of
Yes.
light.
But wait, your answer is still not correct. Okay, stars are far, infinity. They are point sources. You see like this, what you are seeing. If I change it with a planet, firstly, you won't see so much of twinkling. But remember, atmosphere is same whether it is star or planet. Planet is a little close by, that's why you can see the disk. Stars, you can't see the disk. But remember, planet also is sinking. In fact, if you have experience of seeing a moon, the craters with the telescope in the night with a very turbulent night, you will not see the craters very sharp. So scintillation is taking place for planets also, except that it is illusion. It's a bigger object, so you think, no, it is not scintillating. But actually it is scintillating. So the answer is yes, it is scintillating, but you don't see it because comparative to star, it's a much bigger disk. That's all, that is the answer. Okay, coming back here. So what is happening? I said I focus it on the slit. But you see, I can't focus a point of view, it is this light, fuzzy thing which I am focusing. So sometimes the light is here, sometimes the star is moving, so and also drifting. So you may not be picking up all the light, always. And with all this process, ultimately, you are forming the spectrum. So each bin here, if it is CCD, you will see the red pixels showing this kind of thing and the blue pixels. So this is the spectrograph plane. Okay. For the real star. So in the lab, you won't do this. Lab, you will find a very fixed source. Nice, you will see only spots here. So now let us start defining some basic definitions of spectroscopy. Now, the first thing is resolution R, which is lambda by delta. Lambda is the central wavelength. So we saw previous plot. Oops. So here I said R, central wavelength is this or this, and this is 1000 angstrom. So lambda by delta lambda. So this is lambda by delta lambda. And usually when you are doing photometry, which we were talking till now, photometry is this R is less than 10. You can see the example already now that in case of photometry, the 1000 angstrom was the bandwidth and the central wavelength was whatever. So it is R is less than 10. Next is low resolution spectroscopy. Now we are improving the resolution. So instead of BVR, we are taking more and more points. So now the filters are not 1000, they are even narrow, maybe 100 angstroms or even narrow 10 angstroms. So we'll have many points along the black body to observe. So it's called low resolution spectroscopy, or some people may call it as narrow band photometry. Why narrow band? Because they are no more 1000. And the next is medium resolution spectroscopy. Now that R is between 100 and 10,000. Each of these we will see the examples. And last is high resolution when R is very high, more than 10,000. So this is a concept which actually came from a French astronomer come was an optics person. And the biggest difficulty was translation from French to English. The French, I told you yesterday that this word will again come. Now this is the luminosity or the output of the instrument or throughput. Suppose this is a black box, which is the instrument, 100 photons come, whether I can detect 10 or all 100 is a kind of a output of this instrument. So he defined it as attenuation in centimeters square per stellar. But the basic meaning was throughput. This is the French one. And he tried to prove this, that the L of this instrument depends on the area collected by the spectrometer and the solid angle field of view. This is omega. And he said that this multiplication L into R is constant. A way to understand this quickly is everybody has done, I think, sodium D1, D2 line experiment in your right? You had a slit and you can do it visibly or otherwise. If you make the slit very narrow, you will see two D1, D2 lines. And if you make the slit wider, you stop seeing them very well. What happens is, so I will give the example of your BSc experiment. Here, this is your x-axis wavelength, and these are the five eight nine zero, 5896. Now, if the slit is very narrow, you will see them like this. Okay. Now, if I widen the slit, I will still see this. I will show it with a different color. Now it will look like this. You will see it as a dip, but it will be much broader. So see what is happening here. This, of course, in the experiment you did all that. But if you think a little deeply, what is actually happening is when the slit is narrow, light coming through the instrument is less, but you are seeing a much higher resolution. If the slit becomes wider, you are accepting more light, resolution is coming. So essentially, this person called his name I will just remember. It is in the he has written a book also on that. Jacquino. So he said that L cross R for that particular experiment in your BSc on the optical table is constant, which is simple. If you reduce the slit width, you are accepting less light. The output of that spectrometer L is less, but resolution is high. Multiplication is a constant. If I increase the width of the slit, I'm accepting more light, but the resolution is down. So L plus R is constant. But he also said for certain instruments, this constant itself is different, which means for prism, L cross R is some number. For the next level grating, it is much bigger. We will see a comparison. In fact, some student was taking a mobile photo of this slide, which is good. Of course, you will get all this. This you won't see in any book. I mean, it will be there sketchy somewhere. During my PhD, this was my main thing I actually developed was a spectrometer. So I went thoroughly to this. So the next slide. So of course, before I move to the next, this is constant. They have removed the so their area has been made common. With grating, you have this height of the grating area and focal the camera lens with February. But now, for example, this one, the last line is important. February versus grating. To put this is 100 times more luminous. If you understand the word luminous in this way, then it is easy because otherwise attentive is the French word for. So all he says, if you are doing sodium D1 line with a grating instrument and the February, which is a much higher resolution, since the constant is different for February, you will get much better output with February, almost spectrum. So which means if I am doing a spectroscopy with a grating of Orion nebula, so now I am slowly also. So the Orion nebula is actually a nebula like this, right? And it has a green line, and some of you just popular if you have seen a telescope with a telescope the Orion nebula, which is usually seen in January. If you spend a little more time, the sky is good, it looks greenish. Because this is a oxygen 3 ionization line which is coming out from Orion. And I'm not talking of the Doppler and other things, it will come very soon. Let's say that you see the Orion nebula and this color of light comes out from the nebula. Not from everywhere, but patches of. Because that is a very prominent oxygen line which is excited and this line comes. Now, if this line is to be observed with an instrument, you can either use a grating instrument, but then you are wasting time on other methods. Your interest is on the ideally you should actually make an instrument which is just observing on this way. And that's where February will come in the advantage, and because Orion is a bright object, but you can have this addition in other levels. So you would like maximum output of the instrument to be tuned at that specific level. That's where it becomes an advantage. So in this slide, I just basically summarized whatever we talked. Increase the slit width, more light is accepted, but R goes down. Reverse means if this is slit width is narrow, less light, but resolution is improved. But this Jacquino said that for some dispersers, for the same value of R, it can accept more light. That's why it is more luminous. No? So L cross R can be fully. So there is another thing. All this business is theoretical, but when you actually couple with the telescope, you have to take care that all the light from the star has gone through all this. So that becomes a second level challenge. We will not go into that. This is again a comparison. Now suppose area and resolution are same, then for February we will get a much better. If this is comparison with the grating and February. And if I make area and luminosity similar, then I will achieve much better resolution. And the last one is also extremely important for astronomy. Because if these two parameters are same, I need a very small instrument, which is a very light instrument at the back of the telescope. This is the same thing I showed yesterday, but now we are talking about spectral lines, D1, D2. So these are the two lines. And again, the same Rayleigh criteria. How would you distinguish two lines? Remember that in Orion or in other cases also, if there is a rotation involved and there are two spectral lines seen, the other line could be faint. So as I described yesterday, it could be just a kink. It may not be to exactly same intensity. But very fact that you have seen a kink on one side of the wing, depending which way the nebula is, the gas is coming towards you or going away, you are detecting motion within that. Okay, now these next two slides are extremely important. If you want, you can take a picture, but you will get the PDF. This you will not see in any, because I myself created these slides. So now I'm compressing prism, low resolution, grating, interferometer, high resolution. All the three categories. This is based on refraction, prism, holding a prism, diffraction, because light is not suffering diffraction, and lastly, this interference. For the moment, you have to go deeper to understand this, but let's say in prism, all the light comes and it just forms one single spectrum. There is no confusion. Nicely, Newton could see that picture, that spectrum is seen. Different types of material is there. Glass will not ultraviolet, not allow, but you can have certain salts and things made into a prism. They can allow ultraviolet to deep in the light. And they formally are below 500, so they are low resolution. This at the moment forget. But grating can work from X-rays to microwaves. And they fall in this R between 500 to 10,000. And anything above 10,000 fall into high resolution. And here it could be a February or a Fourier transform. So I will not be basically, depending on the time I have, I will probably discuss February, but the books I will refer describe everything. This is the continuation of that table. Now this R, remember the Jacquinot L cross R is constant. You see that L cross R is improving here on this column. They attend you the same bench one again confuse you, but the output is worst. This is better and this is best. Again, you can't compare just like it, isn't it? But the hidden thing is that you are talking of that specific line when you're observing. Then these are giving much better output. And this is where the L cross R product 10 to 50 and this is 300 to 500 times this. This is the last column is the most difficult part. The first one for prism, obviously direct and unambiguous means you have just nice one spectrum sitting on the wall. Okay. Next, so you see what is happening, you are demanding higher and higher resolution. Now the spectrum recovery is ultimately you have to work, analyze the spectrum, becomes difficult. Now the problem is, there is not, in case of grating, medium resolution, there is not just one spectrum, there are several spectrums sitting on the sides. There is a lot of overlapping problem, we will see that. So you now need to really filter out and just the particular spectrum you are interested, you are going to observe that. So it is already becoming difficult because the spectrum recovery, you will do a lot of tricks to do that. And the last one, you don't even see the spectrum. Either, so it's in a Fourier domain. Either you do deconvolve it or using inverse Fourier transforms. So the last section was really a challenge 30, 40 years back because the computers also were very slow. In these last 40 years, very fast Fourier transforms have developed, two-dimensional and all that. So that computation is no more a limitation. Okay, let's see. I will, before I go, okay. So any spectral line, take this. It doesn't matter whether it is an absorption or an emission, right? Mostly in the stars, it goes to regular absorption. What is this? This is a typical spectral line. And the area under the curve, that's very important. I actually ask sometimes my students to do this on a good old way on a graph sheet, millimeter graph sheet. Count all the small millimeter, 1 millimeter. And actually you can make an equivalent line. Right? It's very simple because this area under this can be always represented by a, and ultimately what is happening is you're assuming this to be the width of that spectrum. That's why I've written W lambda. So this is the concept of equivalent width, and this has many, many implications. I mean, I will not cover it, but Shannon might cover or somebody may cover. If you do an equivalent width measurement of any line from Orion or any H alpha line, you can actually tell how many of those molecules or atoms are constituting this line. So you can talk of now the line depth, and you can talk of the number of molecules playing with that. So this is a very useful concept which is used in spectroscopy when astronomers are doing spectroscopy. There are other things also. So I will go back now. So let's see. So this spectral line which you see here, there are four possibilities. First one is natural God, which means everybody knows quantum mechanics, okay, uncertainty principle. So there are two levels in which the transition is taking place. The atom goes to the higher level, stays there for a while, and then comes down and emits a photon, H. That is the natural body. And these two levels, I have a picture otherwise. So these two are the levels where H is coming out. And these levels themselves, because of uncertainty principle, are not sharp. If they were sharp, you will see a one single delta function, which is not, in real life it doesn't happen. Because both these levels have uncertainties. Just for schematic purpose, if you assume one of them as ideal, but then you will have a thing here that is simply energy level spec, which will give frequency spec. Because the level can be back from here, 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 and corresponding the frequencies will also. So usually, natural broadening is always there. And you can observe it, provided the atom which is emitting is cooled down. So people have done this in laboratory spectroscopy, they have cooled it to, I don't know, liquid nitrogen or even cooler medium for the Kelvin. And they have found that you can see this broadening, which is proving that uncertainty principle is there. And the next thing is Doppler broadening. Now I will explain you before I talk about Doppler broadening. Doppler effect itself is a generalized thing. Doppler broadening and Doppler shift are parts of it. So I want to spend a little more time on this. Other things are not so important, but this concept should be clear. So firstly, take the example of anything. Take the example of Orion 5087. So ideally, it's a delta function, but it is not because of uncertainty principle. It has some broadening, and this broadening is called the natural broadening because of uncertainty principle. I explained you why. The next thing is if the gas is, if the atoms are at temperature, then they tend to broaden this, and then it will become like this. It's not on the same scale, but this is so. This and sorry, this okay. That should have been the white color. And this is so. There is a delta lambda n natural, delta lambda Doppler. And typically they are a factor of 10 or more, depending on what temperature. These are the basic things which have always happened. So this tube light everybody would have changed at your home. Change the tube light. It's a little warm, right? The LED tube lights are not fortunately. So very soon these will be out of fashion. So some of them might be already in this. So they are slightly warm. So the room temperature is 25, they are around 30, 35. So because the temperature is a little warm, that mercury atom temperature is that about 30 centigrades. So actually, if you take a spectrum and use a resolution high resolution instrument, you can measure this one, and from that, then estimate the temperature. Exactly the same thing you can do with Orion in astronomy. So this I explained. So this is again slightly not really in scale, but you see the shape, this inner one, this curve, which is having a long wing, is the natural one. It's called Lorentzian shape. Whereas the Doppler modeling is our Gaussian shape. And Gaussian file drops very fast. This I explained. And this is, of course, the example of a line at 6,000 angstroms, the red line. The width, delta lambda, natural, 002, 2 milliangstroms, very small number. So, this is what is happening in Doppler effect. Now, firstly, Doppler effect has both parts, shift and broadening. Shift, everybody has understood because you have from school level a train coming, approaching the whistle becomes sharp and then comes up. So the frequency shift. But the picture here, this is in a book by Thorne. I will give the reference. A beautiful book on spectroscopy. Except a few pages where there is some mathematics. This book actually, I was for some reason one night I had to do it, so I just read that book like a novel. It's a beautiful book written by a British Annie Thorne. So it's there in the library. I can give, and I think many of these books are available online. So you see, this is the human eye looking towards collection of these atoms. Some atoms are coming towards you, some are going away, and that's how you are building the line. And also color is there. If they are going away from you, then it is blue shift, and if they are approaching you, it is red shift. So slowly you form this. This is the Doppler product line. Okay, this is actually what is happening, atom by atom, collection of boxes. So similarly here, if you see this, some of the mercury atoms are probably approaching you, some are going in that enclosure of that gas. So that is giving the product. Shift, how does it? So 5461 is the written in the lab, no shift. If I ask one of you to run with this tube light at a high velocity, then what will happen? All this thing will shift. Now it will be Doppler shift. And in nature, both the things are happening. Here you don't see the shift because this is stationary. But Orion Nebula is also moving. So that five, what was that number I said? 5007. Right? So 5007 is the lab reference for that oxygen. But actually, I don't remember, you can check. If it is a receiving nebula, then it will be shifting towards red. And if it is approaching you, it will become the red will become small. So 5007 will have changes. That is the overall shift of the nebula, as if the tube light, it's an overall set of gas. Now, within that, also there are what you call motions, relative motions. So, if this is my nebula, Orion Nebula, overall light, if I see, it will be 5007 going this side or this side, depending on the whole thing. But within this, now suppose I can take spectra of this part, small parts, I will see that this 5007 line will have these kings, different kings. And if I can resolve it even better, then actually I can see the lines really being shaped. And that is where high resolution imaging becomes important. And people have seen these things and seen that there are, within the nebula also, there are relative motions. This is just, I'm skipping this fast because this is usually the formula. You put the relative temperature, this is the width of that line, some constant. This can be derived in that book, it is there. And M is the mass number of the emitting species. In case of mercury, it will be 198, in case of oxygen, it is 10, and so on. And you can see that was 002, now this is 03 angstroms. In case of iron, in sun has a lot of iron, and this temperature can be derived from this. And during eclipse, people have made observations of corona. Corona is not this height, it is much higher. They have actually used the thermometer to image and do this kind of relative motion and so on. And it's a Gaussian shape. This effect is not normally seen. In the lab, it is seen, but you have to have very strong magnetic. But in nature, particularly in some stars, have very strong magnetic. Usually the sunspots or star spots actually are having much higher effect. They are also cooler. So this is a blue line, zinc line, and this strong magnetic field, you can see the split. So now all the three effects are there: natural, then broadening, and of course it will split with strong magnetic field. And in fact, there is a star called Bernard star, which is 30. Okay, before that, what is the magnetic field here? Anybody? Yes, school or somewhere you are in Gauss on Earth, where you are sitting now. How much? Again, wild guess, tell me 10, 100, 50. How do you know on the surface of sun how much it is? So here it is half a Gauss, average, but there are possibilities. People have all these stories about Bermuda Triangle where the narrative is very strong, but that is not what we are discussing. But yes, near the poles will be little better, but not more than 0.6, 0.7 that. On surface of sun, it is 1 Gauss. Not much, but on the hot spots or the dark spots of sun, or that matter any star, the magnitude is much stronger because there is a concentration of frequency there, and then it can go into kilowatts. So I will give you an example of a star. Right now, there may be more in future, but that one has 30 kilowatts. So 30,000 Gauss means 30 Tesla. It's a huge magnetic field. It's not easy to simulate that in the lab. So again, for that, now it is another factor of 10 now. And then 10 line, and this is the language vector. So you can actually calculate in Gauss. And as I said, some stars usually have about kilogauss or sometimes have to. This is another thing, the rotational is, I don't know whether I'm covered, but there are two things here. Now, this could arise due to two things. One is the star itself is rotating and has some dark spots or some things where, or there are two stars, they are so close you can't distinguish them, but they are moving around each other. And there are two lines, say alpha line, whatever. The lines are like this. They are going like this and going like this. So this whole spectra is continuously shifting. Why? Because one object is occulting the other one, when they are overlapping, you will see this. So from that shifts, you can measure the. So this is rotational part. Simple concept, but it's difficult in observations to do this, but people use this. I think I will not go into too much detail, but in spectroscopy, just like explaining, the prism here is the disperse. These are the actual definition. And the purpose of disperse is to disperse the light in different wavelengths. That's why it's called separate wavelengths by spatially spreading the sound. Spatially spreading them of neutral mode with the prism to see the spectrum. And the measure of spreading is called dispersion. Angular is d theta by d lambda. Every angle has that wavelength. Linear, if I put a lens, then focal length comes in the picture. And now I can tell each distance, this is the lambda 1, lambda 2, lambda 3. And the reverse of that is useful because ultimately you want every millimeter what is the spread out in angstroms. So reciprocal dispersion. I will move in somewhat possible. This is how the grating looks. Very typical grating. Grating is actually a glass. Olden time, but now there are substrates and they have holographic gratings. And the original gratings were actually done by diamond, and this is a cross section. And you can't touch them because that it's spoiled. So it's very expensive process. They used to make images of that on, they call it, they use it, I don't know the procedure, maybe photography or just like the thieves copy the key on the wax, something like that was done to make copies. The original grating is very rare because it's a one-time thing. So essentially, this surface is a mirror, but just these grooves provide this extra effect of what is called diffraction. So this is what is happening. This is just like a axon. So there is a normal. This N is as if this is a mirror. This is the grating normal, and this word called base, they make it efficient in a one particular direction, which means incoming beam, outgoing beam, and this gap between the groups is D. So this is very well explained in that book, and there are several other books. All this formulation of grating. And I was telling you, so this white light here is as if this was a mirror. It will exactly go out, sign incidence and reflected. But these other colors, the blue lines or here, this is the blue side and red side, are the other spectra which are happening. So now actually you can design these groups in such a way that, so these are called orders. This side is one order, this side is another order. You can maximize in first or second. And others, the efficiency is less. So what you can do, you can actually filter here and here and use only the one where you have maximized. And that's why to remove. So it becomes already difficult because you have to take only the spectrum which you are interested. There will be multiple spectra sitting at the same point, but factor of 2 or factor of 3 in your skip this, skip this, skip this. So this is a huge CCD camera where sun spectra is taken. And Eshel is a technique where you can take the complete spectrum starting from red to the other side in beams like this. And you can see these final lines, sun spectra. It's a G-type star, so these are the absorption lines. So in principle, sun is the bright objects. You can take a spectra like this, but for stars also, if you have a sufficiently large telescope, in one go on the CCD, you can take the complete spectrum. I will run through a small example of designing a grid. So suppose I have been given a 2-inch 50 mm wide grating, and it's called monochromator because you can divide the light into monochrome, each single wavelength. And 1/4 meter means the collimator length is 250 millimeters. And this is the groups, 1200 lines per millimeter, and it is glazed. The efficiency is improved at this in first order. And these angles are 17.5 degrees. So what you have to find out is the reciprocal distance, because ultimately you are interested on the CCD or the photographic film. Every millimeter is how much wavelength. Then the theoretical resolution, because you will never achieve the theoretical. Ultimately, you will have a resolution with a split. In this case, it's the CCD and the size of the pixel touches 6 cm. So these three things you have to find. Simple calculation. You have all the numbers here, pitch, 200 lines per millimeter. There is the group spacing, phase wavelength, order is 1, width of the grating is 50, focal length is 250 millimeters, and this beta is the refraction. So this is the first formula which you use. These are all derived. You have 3.2 nanometer. Means 32 angstroms every millimeter you have divided the light. This was the light into 32 angstroms, right from lambda 1 to lambda. Theoretical resolution is straightforward, so it is 60,000. So it's in the high resolution, not very high resolution, lambda by delta lambda. But actually what you achieve, you can shine a laser, which is like a delta function, and then what do you get? It will broaden out, and what you get is actually this 0.9, which is 1 angstrom. So you have deteriorated from the theoretical to the real achievable resolution is only 1 angstrom. And this is why the R is 65. Okay, now a little bit about the actual observation. So this is an instrument which any spectroscopist who has done astronomy, at least in our times, now of course these telescopes are not there. This is in Arizona in US, in Tucson, outskirts of Tucson. This is a telescope which is a 0.9 meter, 1 meter diameter, and this is the most used telescope for doing spectroscopy. Rather, any veteran spectroscopy person would have got trained or used it. So we used it for many years. Actually, we developed a US collaboration with a very large library of spectra of some 1200 stars, hot and cold stars. And that library is used even today. So what is happening is the star light comes, hits this 1 meter. Then there is a reflecting mirror which brings the light here down. And this is at the terrace. These ratings are there, you are not supposed to go there, but towards the last observatory runs, there was more support available. So we got some donations to run the telescope because we could not complete our full 1200 stars thing, so some were remaining. So we actually went there and it was paid observation. And this was already aged now more than 30 years of observation, so things were paid. So once or twice we went up, which was not legal because if you fall down from there, you can sue them. So, but then we took chance and almost literally, things were not coming in the focus. Then the light comes from that terrace, comes down here, where you have all the lamps, because the spectra has been taken, but you have to calibrate what is the x-axis. Whether you have the blue or red region, you don't know. So you have to have spectral lamps like mercury and other whose wavelengths are known. Then the light goes down further into a room of this size, where you have the huge gratings. And further down, the light comes and there is a CCD detector controller. This is a cylinder. It's like your Earlier it was Eagle company made this glass flask for your cold around, but now we have steel. So vacuum enclosure inside liquid nitrogen is there to cool the system because you want to bring down the dark clouds. And you can barely see there is some vapor coming out from the nitrogen. And this is such a stable instrument only once in the night the operator will fill the liquid. Then again in the morning. And this CCD was a special CCD. It was 1000 angstroms by 3000 angstroms. Specially made for spectroscopy. On this side you have the spectrum, and this side you have the sky. So what happens, the CCD in the central side of the pixel you have the spectrum, and rest side are the spectrum from the sky. The sky light also has some brightness in the night, so it is used for calibration. Those lines are known. And this is the example of the actual spectrum. This central one looks like a noise. This is a K-type star, which is at around 5000 degree Kelvin, a yellow star. And these are actual lines in between. I have expanded them. So these are real spectra of a star, which is very high resolution. So we took O, B, A, F, G, K, all about 1200 of such stars and their spectra. This become a big library all the way from almost 3000 to 9000 angstroms. The more use of this is to calibrate your other spectra, but more importantly, you have synthetic spectra. Again, I don't know what you have to discuss. If you have a globular cluster or a galaxy, galaxy has also globular cluster has all types of stars, young and old, hot and cool. You will get a net spectrum. Now it's a challenge to have such libraries you mix and match them to get that net spectrum which you got from the galaxy. So it will only tell that you have a number of hot stars in that, so the galaxy is older or younger, so evolution, all those things come. So this kind of library is called synthetic synthesization, and a lot of people, evolution and all, they use these libraries. So after our work, which was more than 30 years back, now many more libraries have been formed and so on. Now we don't have much time, 5 minutes. I will just explain it briefly. This looks like the Newton rings you have all done. This is also similar thing. It's two glass plates. The inner surfaces are aluminized, very highly polished and aluminized. Outer are not. And I told you outer have to be ARC coated because every surface the light comes, 4% loss is there. So it has to be reduced. So you will see this kind of rings. And this is what is happening, the light coming from an extended source. It's multiple reflection. And you use a focusing lens or camera lens, and you have the fringes coming here on display. That's how these fringes look. And what happens is, there are two ways. One is, of course, these have to be perfectly parallel. If I do this, changing the width, changing the separation, you can't do this because then the alignment will. So it has to be perfectly moving. So these rings will either go inside or come out, depending on which way you are. So essentially, each one, this is a diffuse picture, but there is a spectrum like this. It's a continuous series of, in the center there is a hole. If I have a detector here, I will see the peaks moving one by one as the fringes move. So again, not going into much of details. N lambda is the which ring you are doing. This is the wavelength. You can change by changing the refractive index, gap, or tilting. This refractive index changing was easy at our time. You could put the whole thing in a chamber and pressurize. If you pressurize mu, delta mu, so delta P by P, you are changing P over which you are putting delta P by the piston. Delta P by P is delta mu by mu, which is delta lambda by lambda. So by changing pressure, you can actually move the rings on the center. Then, almost the time when we were completing our PhD, this changed. So you can do one at a time, of course, not all three to change lambda. T was coming up. Now, this is a challenge where two plates have to move, as I said, keeping the patterns. So this was developed by an optical engineer and an astronomer. They use what is called piezoelectric motion. So I'll take a bit while to explain. This is a very challenging technology where, as I said, now you can. I am showing you the side view of this, and the coated area is here. And this is the gap, T. Now, just to move in such a way that it retains the parallelism. So now I will show a cross section from top. This is the outer thing, and inside part is coated. Okay, this is the coated part. Here, there are two diameter of it, CX, CY. These are just two small patches of coating which act as a capacitor. Any change in capacitance will be sensed and the computer will make it correct. But how will you do it? There are three spacers. So these are actually spacers are this kind of material with these are piezo. Piezo material, if you put about 1000 volts in a node, it expands and contracts. So which means three piezos are here, symmetrically 120 degree, and this CX, CY, any change, electrical pulses are given to these piezos to make them correct. So essentially, it's a feedback system which maintains. And how do you connect these piezos to the surface? These surfaces are very well polished, almost to the wavelength of lambda by 100. So what they do is, this is a technique which was developed about 20 or 30 years back. Optical contact. What they do, this surface and this edge is polished to that or even better. And then it is brought here and molecular bonding takes place, which means unless you give a jerk on this side and this side, otherwise it will be locked there. Molecular bonding takes place. So you fix that and do this looping and maintain it. People can maintain this parallel thing to the order of lambda by 10. This is enormous thing. And you see this unit sitting there, you put a light at the bottom, a sodium light, you will see the rings, and you actually literally you can kick the table, rock steady, and the feedback thing works. So this was the technology developed, and then is much faster because now you don't have to have the pressure and all that, and you can do. So this was called the spacer scanning. I will skip most of these things. There's a lot of physics there. I will just want to popularize myself. This was so February is actually a 100-year-old technique, 1900 something. February was a French, Perot was French and February was British. They both, the name is that. But since Perot was French in France, they call it Perot. So this parallelism was never analyzed thoroughly theoretically. So we developed this procedure and this was a publication there just around the time when I was joining. And this function was not. Just one more thing as a last parting thing. Any random phenomena usually is described as Gaussian. So suppose you have a glass and you use corundum powder to make it as a ground glass. The distribution of the roughness is a Gaussian function. Anyway, so let's skip this all these things. This is how the fabric actually looks. We have one of them here. There are some electronic controls here, and this is the spacers here. And this is the thing from the side. And inside, you can barely see the bridge line because the thing is there. And these are the outer surfaces. I will have to run through this. So when you go for observatory, you have to observe, let's say, a set of stars. They are called program objects. And it should be available in that part of the night and that part of the Earth where you're observing, so it is India or there. And you should have a standard star because if you're observing a star which is varying and a standard star, it should be the same region. Otherwise, the light is coming through a different part of the atmosphere, so you can't tell. So all these things have to be taken care of. It has to be sufficiently bright. And if you have fainter observation, then fainter standards. Then what kind of grating and vision you have to know well in advance which lambda 1 to lambda 2 you have to observe. And also the lamp, because you have to calibrate the x-axis. So this is the procedure. You take a lamp, spectra in the evening before it becomes dark. And also you have to see the CCDs are good in the infrared side. I said it's a silicon device. Blue side is less sensitive. So you have to take a white light spectrum, which is halogen bulb, and correct for. Then observe a standard star. Then observe the required object. And some tools are there, software tools developed. Now, of course, Python can do this, but those days IRF was there. And use that software to analyze and get the set. So I'll just show you some snaps. So this is actually a helium neon lamp. So these are many, many lines on the right side. So these wavelengths are known. So your x-axis is calibrated actually. So that this is the halogen lamp, and obviously this side is dark. There's blue side, less sensitivity in the CCD, and also halogen has a particular temperature, so it's a black body kind of thing. So you use this, and this is a standard star spectrum. You can fairly see some dips. So those are, I think, this side is the blue side, HL will be somewhere here. And this side is covered by the sky. The star is sitting on the slit only on this line. This is the actual observation in this case, not supernova. So how it looks, so this is the calibration thing. These are many, many lines of that helium neon lamp. And the wavelength comes because the people have observed it, so the software knows where what is there. Then this is the sensitivity curve. As I said, with that white light we have done. So this side is new, less sensitive, this is more sensitive. So this curve is used to reverse the thing. Which means now this is how the actual star will be. The standard star is a blue star. H alpha is 6563 somewhere here. This is H alpha, there are other H beta and other lines. So this spectrum of the star has been taken by several observatories all over the world. So people know the x-axis. You are also observed, you know your y-axis. You cannot calibrate this. Which means now you know at this position what is your sensitivity in terms of magnitudes. And then this is the supernova spectrum. Okay, this is the last slide. These are the set of books which I would recommend. This is a very basic book on kitchen. This is another book. This is the book I was mentioning, A.P. Thorne. Actually, it's there in the library. This is a book on Pelvipero. This is a very important book which discusses most of the things, I told about the CCDs and kind of things. I think this is the latest version. There were earlier several. There is a classification book. And lastly but not least, this is online available now. This is a review book, which is, I think you can buy the hard copy, but now it is online. It's a set of 7 books, and we were asked to write chapters. So I have 2 chapters on this. The whole idea of this book was that there is no teacher, a self-reading book. So with examples and all that. So I would urge you to see this review book. Okay, I think I will stop here. Can I have a few questions? Let's see whether chat box. Let me first clean this chat box. Any questions?
What do you mean by the standard star?
Okay, she's asking what do you mean by standard star? Standard star is not fluctuating. It's a star which doesn't have a companion. Again, just to go deeper into your question, all stars are not standard. Some are standard. But suddenly a powerful telescope comes, you start seeing variation that will know. So yes, as of now, there is a set of stars, standards and all, which are available. But the way things are, the technology improving, even that definition may change because that particular star you say standard, 10 years down the line, somebody may find that it is fluctuating. So yes, standard star is record because you need to know where is your baseline and then you have to see the fluctuation. You have to have a standard star. All questions?
Why do we use blue and violet colors of blue PV filters?
It's a question is not clear, but I can answer it quickly. We have seen B and B, but I also hinted you can use BLR. Any 2 minimum you need. More the better. So the kind of question I asked to the see last week when we had exam, I asked them to draw one blackbody curve of 3000, one for 6000. The first mistake they do, the blackbody curve is crossing each other. That will never happen. Number 2, if you have 2 filters, if you have just one filter, then many blackbody can pass through it now. So I tell them that one filter is broken, can you do this experiment? They said yes. I said how? But they don't realize that many blackbodies can pass through. Unless you have the second color, you can't lock that blackbody. More the better, or narrower the better. But minimum you need. Anything else?
When you have artifacts in images, are they due to the saturation of the CCDs?
Your general point is artifact in images, but it can be of different type. One is something called defects in the CCD. So even the perfect CCD they are called cosmetic defects. One pixel can go bad after some time. Original, the freshly made, some of the CCDs which are engineering grade are used for only checking the instrumentation. There are many pixels which are bad, but which are grade 0, which is almost no defect. It's very expensive because they scan some hundreds of them and the best ones filter. And that's why the cost goes. That itself may go bad after some time. Number one. Then artifacts could be of various reasons. They call it bleeding. Some pixel, as you say, it is more saturated and you will see a line like this. So that particular part, if there is a star sitting, you can't observe because it's saturated. So yes, there are many artifacts happening in the CCDs and they are not perfect, but yes, it's difficult to maintain. You have to keep them during the non-observing time. They have to be vacuum because the humidity can affect the sensor. So artifacts are there.
Could it be that the starlight is powerful enough to oversaturate the
starlight is?
The star in the background or something. It's very
Yeah. What he's asking, in a field, suppose there's a galaxy, but there's a star which is very bright. So you are right, that particular pixel will be fully saturated. But you purposely do that, go deeper, more exposures to bring out the galaxy. So that part, since is all digital, you don't use that part of the X1, Y1, that part. So yes, that is also done. Because then as soon as you do piping, some will saturate obviously with the brighter objects in the photo. Just to give you an interesting answer to a question similar, our main research, one of them was where stars are found. Dark clouds, dust or collapse. Stars are found. So there, the object itself is dark. Periphery, some stars are there which recognize the operator in the night doesn't know. So I tell them, okay, one star here, one star here. This is the picture. You try to see whether you have caught the object. Even though the R&D, everything has been done. He said, sir, there is nothing there. I said, that is my object. Because it's a dark cloud which is forming. So what I do, periphery of the dark cloud, starlight comes through the dust. Deeper inside I can't do unless I do nothing. So I now measure the polarization. And for polarization, I can talk what kind of dust, magnetic fields are there, various things. So that was our main research some 10, 15 years back, and we did a lot of work on that. So since these are dark clouds by definition, need bigger telescope. Because at the most, foreground stars will be bright as magnitude of that. So those you can anyway remove. And also they will not be extinguished. The dust is after that. The stars which are behind 15, 16 magnitude are most probably the ones which are behind. And that light creeps through the dust. And because of that light has come through, you can measure the polarization and talk about the dust and so. Yes.
Actually, sunspots appears on the surface of the sun.
Sunspots appears
on the surface of the sun. So why there is different magnetic field for both the surface of the sun and
why there is different
magnetic field for surface of the sun is 1 cos 6.
So I told you, firstly, the sunspots. You can ask this question to Gupta who talk on sun. Firstly, sunspots are cooler. Number one, but they have concentration of field lines. Because the magnetic field structure of sun, the field line comes, goes to the next spot. It's a very complicated thing. So they will be talking about those pictures they will show. And because the field lines are concentrated, the magnetic field is stopped. Can be up to kilowatts also. You ask them this question, but I've given you the first level answer. And sun, like sun, stars also have stars. You can't see the surface of stars because it's a point object unless you do very interferometry, and there are some ways of doing it, and some people have done it. It's a very rare technique and difficult, only bright stars. Any other? I don't see one. What are importance to analyzing gaseous vapor in spectroanalysis to detect object in gaseous form? I don't understand the question, but probably the person is asking. solar dynamics to structure analysis. So anyway, the first question is, it is a gaseous thing like nebula or something. You see the spectral lines, so you can analyze the motion, which I already explained by using high resolution spectroscopy. The second question is solar dynamics through spectral analysis. So this question you ask to the person who will talk about solar thing, but the basic thing is same. Solar dynamics, the sun is closer, you can image the surface of the sun to a great extent, and you can take the spectra at each point. So you can talk about the dynamics just like the Orion dynamics. If there is any other question here. Otherwise, they can always ask me on this thing over email. So thank you, and I think we will break here. This was my last call, but I am open to any questions later on over the email. Okay. Some of you are doing, or all of you are doing a summer project, right? You will be doing some projects with the faculty, right? So have you already decided what you will do? Because we have a limited time to the projects. Is that right? You are doing a project, right? Sometimes two students together.
We haven't been told anything. So that's
Haven't told anything.
the project one. That's what the mission student program. The 6th and the 6th student.
No, because I thought usually this summer program has double thing. One is the online fellows, I don't know what they're doing, but people who are physically here are supposed to be doing the project also.
And they've not told us.
First, today is the second day, but very soon you have time. Because you will have a presentation of your projects first. Okay, thank you.